Welcome back to this video tutorial. We can consider one more problem regarding memory interfacing. The question is design and interference between 8086 CPU and two chips of 16K by 8 EPROM and two chips of 32K by 8 RAM. Select the starting address of EPROM suitably. The RAM address must start at 0000H. So given the RAM address must start at 0000H and the size of RAM and ROM are different in this situation. And for selecting the address range of EPROM, here it is given as we can select the address range of EPROM suitably without any restriction, but we need to consider the condition. After resetting the ROM, the processor start from FFFF0H. So always select an address range for EPROM or ROM type memory in which this particular address value must lie. Okay, so here given the range of EPROM, that is 16K by 8, and two such EPROM units are given. So total 2 into 16K by 8, that is 32K bytes are available in our ROM space. 32K means 2 raised to 15 bytes are available in our ROM space. So for addressing each of the bytes in this 2 raised to 15 bytes of a ROM space, we take 15 bits of address information A0 to A40. And for RAM, given each RAM unit with size 32K by 8. Such two units are given. So 2 into 32K by 8 means total 64K bytes are available in our RAM address space. Okay, so total 2 raised to 16 bytes. 64K means 2 raised to 4 into 2 raised to 10. Sorry, 2 raised to 6 into 2 raised to 10. That is 2 raised to 16 bytes are available in our RAM space. So in order to address each of these bytes uniquely, we need 16 bits of address information and is represented as A0 to A15. Based on that, the address ranges address mapping is given here. For the ROM memory space, this particular address always comes under the address range of ROM memory, right? So start from full of 1, okay, and select 32 KB, that is this 32 KB in downwards. So from this particular address F8000 to FFFFF, this particular range actually indicates 32 kilobytes. So this particular range is taken for this EPROM. Okay, so here total we need for ROM memory, total 15 bits are required for addressing each of the bytes in this ROM memory, 32 KB of ROM memory. So first 15, first 15, that is A0 to A14. Okay, so these bits are used for addressing ROM bytes. So full of 0, 15 full of 0 to 15 full of 1s. All address values come under this range are used for addressing byte of EPROM. Okay, 15 A0 to A14, 15 0 to 15 1s. Remaining bits are set as 1. Okay, and from A15 to A19, these bits of informations are used for chip selection purpose, right? So this A15 to A19 is set as full of 1s because this particular address value FFFF0 must come under this particular address range, and all the byte address must be continuous, right? So next is about the RAM address space. Total 16 bits of address informations are required for addressing each byte uniquely. So first 16 bit A0 to A15 taken for representing the address of each byte present in our 64 KB RAM, right? So the address ranging from full 0, 16 full 0 to 16 full 1s. Okay, so address value ranging in this particular range, that is 16 full 0 to 16 full 1. Each these address informations are used for addressing each of the bytes of 64 KB RAM. So here we start the address from 16 full 0 because this condition is given in our question, that is RAM address must start at address 00000H. Okay, so for more clarification, consider this total 1 MB memory, that is 1024 into 1024, total 1048576. And for these much bytes, the address values range from 0 to 1048575. In hexadecimal 000002 FFFFFH. Okay, so among these we need to allot certain space, that is 32 KB for our ROM and 64 KB for our RAM, and RAM must start from 0. Okay, so 32 KB ROM allocation start from, or ROM, we can start the ROM allocation from 1048575 from the end byte. Downwards we can allot 32 KB. So starting from this particular location downwards up to 1015808 we get 32 kilobytes. Okay, so for this particular range, the hexadecimal corresponding address values are F8000 and FFFFF. Okay, that is why this particular range allotted for EPROM memory. And similarly for our RAM memory, we need 64 kilobytes of memory allocation, continuous memory for RAM allocation. And in the question, which is given like the RAM address must start at 00000H. So for 64 KB RAM allocation, we can start from 0 to 65535. Total 64 KB. Okay, 64 into 1024. K means 1024 bytes. 64 byte into 1024 bytes equal to 65536. Okay, these much bytes are available in our RAM space and the address value ranging from 0 to 65535. So corresponding hexadecimal representation is this. This is given here. Okay, so now we can consider the integration circuit for this particular memory allocation. Even odd and even bank for RAM memory and odd and even bank for ROM memory. Okay, and here for ROM memory, how many bits are required for addressing? Total 15 bits. Okay, A0 is represented here, remaining A1 to A14 is used for addressing. Okay, similarly here for RAM we need total 16 bit of address information. A0 is marked here and A1 to A15 is represented here. Okay, and about the data transfer, from even bank always transfer lower byte of 16 data, D0 to D7, D0 to D7. Okay, and from odd bank we can get the higher byte of data, that is D8 to D50, D8 to D50. From the odd bank of RAM and odd bank of ROM. And for ROM memory, the processor can read data from memory. The read operation is only possible with ROM type memory. So the processor need to generate memory read control signal and is connected with the output enable pin of ROM. Okay, so this output enable pin of ROM is always connected with memory read signal generated from our processor. But in case of RAM, both read and write operations are possible. So here we have two pins associated with our RAM memory, that is write and read pin, which are connected with memory read and memory write signals from the processor. Clear? So all these are common with the previous case of memory interfacing. Now consider the situation. Here we need to consider or derive the chip selection. CS1 bar, CS2 bar, CS3 bar and CS4 bar. Okay, and for ROM memory we have total 15 bits of information used for addressing and A15 to A19 used for chip selection. And for RAM type memory Total 16 bits of address informations are used for addressing the bytes and remaining A16 to A19 used for chip selection. Okay, and in this particular case, consider the RAM space and ROM space are not continuous memory. Okay, the ROM space starting from 00000, sorry, RAM space starting from 00000, this is a condition given in our question, and end at 0FFFFH. Okay, and here some bytes are kept as unused, and for the EPROM it start from F8000H and end at FFFFH. Clear? So in such situation, if the memories are not continuous, then we can use simple circuit for selecting chips. Okay, so we can simply use gates, simple combinational circuit for selecting the chip for generating the chip selection signals. So for that, for this particular case, for the ROM memory, A15 to A19 are the chip selection pins and is taken as an input to this NAND gate, and its output is marked here as C. Okay, and similarly for this RAM, A16 to A19 are the selection pin which are taken as an input to this NAND gate, and its output is marked here as C dash. Clear? So we have already mentioned in our previous problem, that is whenever this BHE bar signal equal to 0, then only data transfer takes place from this old memory. Whatever it may be, like whatever it is, a ROM or a RAM, the old memory data transfer or data transfer from higher byte takes place whenever this BHE bar equal to 0. Similarly, for transferring data from event bank or for transferring data, the lower byte of data, A0 value must be equal to 0. Right? So for based on that information, in order to activate this particular old memory of ROM, perform a NAND operation between this C output with BHE bar. Okay, and its output is connected as the chip selection pin of this old bank of ROM. Similarly, perform a NAND operation with the C output of this NAND gate with A0, and its output is taken as a chip selection pin for this event bank of our ROM memory. Similarly, for the case of RAM, for performing data transfer from the old bank, take this C dash as an input and BHE bar input to a NAND gate. Its output is taken as a chip selection pin for the old bank of RAM. Okay, and the same C dash output of this NAND gate C dash with A0 is taken as an input to this particular NAND gate, and its output is taken as a chip selection for the event bank of our RAM memory. Okay, so here C actually indicate output of this NAND gate, and its input are A15 to A19. And for this C dash, the inputs are A16 to A19. These are the chip selection in case of our RAM memory. Okay, so this is the diagram that representing the given memory interfacing situation. Okay, thank you.